Okay, second part this week, we're going to start talking about transporting that energy we talked about from the sun into heat, temperature, and eventually atmospheric circulation. So basically the weather, what we're finally getting to talk about. So let's see what we can find out. So what causes this heat transfer that causes weather? So let's define some terms first. Temperature. Temperature is directly proportional to the kinetic energy of an atom or molecule. What the heck does that mean? All right, every atom or molecule shakes. There's a rotation to the electrons around the center, and the faster they rotate, the more the kinetic energy is in that molecule, or the faster they vibrate, so that raises the temperature. So think about it. If the temperature is quite hot, molecules are basically hitting off each other all the time and pushing them apart. Now, when it's quite cold, the molecules aren't quite so energetic, so they move a little closer together. So that is something to recognize down the road that we're going to talk about a lot in the air. Internal energy, kinetic and potential energy, which arises from just the atoms themselves, and heat is transferring energy. If a molecule hits another molecule, it can transfer energy, heat. So with that, there's a temperature gradient. Guess what? We've already talked about how much more solar energy arrives at the equator than it does at the poles. So there is guaranteed to be some kind of temperature gradient between the equator and the poles. And what we've learned through the years and through study of thermodynamics is that heat will flow in response to that temperature gradient. Basically, the atmosphere always wants to wipe out any kind of gradient. And in this case, it's temperature. So the atmosphere is going to do everything it can to eliminate the temperature gradient. And that means that heat will move from the hot source down to the equator towards the cold up near the poles. And it will do everything it can to try to make that one uniform temperature from the equator to the poles. It can't do it because the sun's always heating the equator more, but it's going to try it. And the processes it used are radiation, conduction, convection, and latent heat. And we're going to talk about those now. Radiation, we've talked about the heat transfer coming through a vacuum, like through space of the sun's radiation. It can also happen through an object heating out, radiating outward. You've seen at a fireplace, if the fire is burning real hot and you step closer to it, you start feeling warm, right? Well, that's radiation. That's heat being pushed out from that fire because it's a hotter temperature fire there, and it's sending out through heat transfer that radiation. Conduction is another form of heat transfer. In the middle of summer, think about walking on hot asphalt. Black absorbs a lot of radiation, gets very hot. If you put your hand down on that asphalt, it's going to burn. It's going to be hot. What happened to cause your hand to burn is the conduction. It's transferring the energy from that hot pavement to your hand. So that is conduction. It can happen pretty well in some instances, but notice air. Air is really a very poor conductor. So when you get a lot of air around something, you're not going to transfer heat real well. That's why when your hand touched, it's one thing. But if you held air between your hand and the surface, you wouldn't feel it nearly like you did. There's another thing in fluids, and the atmosphere is a fluid that's called convection. Ever watch water boil? It's creating convection. Those little bubbles that are coming up are pockets of hot water. So they're convection. They're rising up and they're sinking back down in another location after they've hit the surface at the top, cooled off slightly, and go back down. And when you combine conduction and convection, you get something called sensible heating. And that drives a lot of the heat within our atmosphere. Latent heating is another odd process. All right. Water is the only element in the atmosphere that changes state in the normal temperature ranges of our atmosphere. What does that mean? Well, water can go from a vapor, water vapor, to a liquid, to a solid, or back. And it can even skip a phase. It can go directly from a solid to a vapor. So think about it. If you have a water vapor, the molecules are a little further apart because it's a gas. So they're rotating faster. The temperature is probably going to have a little more energy in it. And if you go to a liquid from that gas, have condensation, what happened? Some of that energy has got to be released. So there's actually a release of warming because the water vapor is going to go towards a liquid now. Now you go the other way. Say you had a pond or a puddle in your yard from after a heavy rain. The sun's just beating down on this hot ground. What you watch is that puddle gradually evaporates, right? Well, you now have liquid that is being transferred to a vapor. It gained heat. So that heating from the sun, instead of going in to heat the ground or the atmosphere, is being used to heat the water, which becomes a vapor. That is why if you've had several days of rain and you get a nice, bright, sunshiny day, that sunshiny day is probably not going to be as hot as if you had no rain. We had a period a couple of weeks ago of we went like 14 days without rain. The ground got really hard. And what happened is it kept getting hotter and hotter, even though it wasn't that much colder, warmer in the air mass. The ground was just pouring in that heat back into the air. So we got hotter. Now, since then, we've had over 7.5 inches of rain. The opposite is occurring. It's not able to get as hot. So that's why near maritime climates, say you live near an ocean, like I do, but better even on the West Coast, take San Francisco, for example. You'll notice throughout the year, there's not a lot of change in temperature. Whereas in the central part of the country, St. Louis, your area in Ohio, if I want to talk about Maine, Maine can have more of a maritime climate, especially along the immediate coastline. Now here's just a diagram of all the processes that happen with radiation coming from the sun. And just wanted to highlight, like, some of it is absorbed by greenhouse gases, re-emitted aloft and back towards the earth. So you can see then there's sensible heat flux from the ground, latent heat from water vapor, and then all this reflection, scattering of radiation, all of that goes in. If you want to calculate the temperature at your house, every one of these processes must be understood and come up with a temperature for you. So heat transfers between conduction and convection are measured by temperature change, or a thermometer. Sensible heat, which includes convection and conduction, you can really notice it in the summertime in cumulus clouds. When they start going up, think about it, that cloud is releasing water vapor going into a liquid, so it's releasing heat. Convection, pushing air, warm air up from the surface. So the two combine to really be a hot pocket of water, of air that's in the convection cloud. And if it can really get going, go up into a cumulonimbus cloud, that warm air is transferred all the way up through the whole stratosphere, or the troposphere, even into the stratosphere sometimes. So this is the heat imbalance that actually occurs, though. You'll notice over the equator there's a surplus of solar energy compared to the actual temperature. So what happens to that solar energy? It's got to be going somewhere. Well, it's used to replace the deficit of solar energy that's seen up towards the poles. So all this solar energy that comes down here is being moved towards the poles through air masses, tropical storms, or great sources, ocean currents. All of this is trying to find ways of moving the cold, replacing the cold air to the north with the warm air to the south. Air masses are just a huge volume of air covering thousands of miles. Tropical storms and hurricanes are great contributors. Then this imbalance is what causes atmospheric motion, what causes showers and thunderstorms, what causes temperature change. And here you can see, think about it during the daytime at your house. In the morning, the sun came up, we'll say right at 6 o'clock or a little bit after. There's a surplus, first, of heat. Now that is heating up your air all this time, even though you got to remember, as the air gets hotter, it's going to increase the amount of infrared radiation it goes. Because remember, the more the temperature, the more the energy is released. And it acts like a black body, the air does, or the surface of the ground. And eventually, there comes a point in the afternoon where they equal. That's when your maximum air temperature occurs. But you'll notice right after that, boy, infrared radiation is at its peak and gradually slows down. That's why the temperature really drops fast during the first couple of hours after sunset, and then gradually drops slower after that. So you can see the same would hold in the morning, where it's going to rise fast at first and then slowly peak. So that's explained everything that's going on in temperature at your house right now due to radiation. Ground cover makes a huge difference. If you have no plants, like in a desert, guess what? The ground is bare, the soil is dry. All that energy from the sun is getting used up by the air to heat it. So it really gets hot. Now, go in the wintertime, if you have snow cover, a fresh snowpack has a very high albedo. Ice over the Great Lakes in the wintertime. All of that reflects back the sun's radiation, and it keeps it colder, especially at night. It really is going to allow it to cool up at night. Then there are urban heat islands. Here was just one conducted. A lot of this is based on the fact that buildings absorb heat, and they wind up getting hotter and hotter during the day. And then during the nighttime hours, even though they're hotter, they release heat differently than the atmosphere through conduction and all, and they wind up keeping it warmer. And I lived near DC for several years, and I can tell you these effects are real. We always, when you made a forecast, you always had to forecast a different temperature, a higher nighttime temperature for downtown DC than where I lived, which was about 15 miles west of DC. So I just wanted to show you a couple quick things here. One of the things we talked about in there was advection. Take a look at the winds blowing here across Ohio today. They're out of the south. And if they're out of the south, warm air is typically to the south. Temperatures are in the 70s down here, upper 60s here. We're actually advecting in warmer air. Out in the Midwest, across Iowa, temperatures are in the 70s to the north, and the winds are from the north. It's advecting in cold air. It's cold air advection. These are two terms you're going to be seeing a lot. So I wanted you to get used to that. And finally, I just want to take a quick peek. Just look at cloud cover. And if you looked at cloud cover and how that impacts temperature some days, this is the current satellite picture. That cold front that we just saw out here has a line of thunderstorms developing or showers developing here. Here's what's left, what amounts to Claudette. Lots of cloud cover with it. And if you go back to the other thing, look at the temperatures down there. You can see that cloud cover is holding temperatures in the 70s. Whereas outside of it, temperatures are in the 80s, almost 90. So cloud cover, big difference in temperatures as well. So, hope you got something out of this. Please don't hesitate to ask if you have any questions.